Lab 2. The motion of a falling object. The purpose of this lab is to observe the motion of an object that is dropped from rest. The object that was chosen for this lab was a lightweight stress ball, since when it is dropped it falls somewhat slowly. In this report, I will discuss the computational model with and without drag force, the experimental model observed from Tracker in comparison to the computational model, and the physics involved. Later you will see that the computational model with drag force closely predicts the experimental model. Here are some important equations that you should keep in mind. Newton's second law, weight, drag force, net force, and updated position. Here's the video of the ball being dropped. The portion that I obtained data points from in Tracker was the 0.5 seconds that it fell from rest until it hit the ground. I set the calibration stick to hit to the diameter of the ball. However, this may have skewed the results since the size of the ball in the video changes based on force perspective. The final Y point, negative 1.082 meters, showed the distance that it fell, and was later used in the computational model as I will now discuss. The computational model was first calculated without drag force and solely the gravitational force, but it underpredicted the experimental model as you can see in this graph, which suggested that there was an upward force also acting upon it. Since there was an additional force, I changed the code for the computational model. Since the code for this model where there is no drag force acting upon the object is so similar to this code, I will only discuss what I added. There is now a constant b, which represents the magnitude of the drag force, and I added the equations Fd equals negative b times ball.vel times negative ball.vel.y, which causes the magnitude to be proportional to the square of the object's speed. And to Fnet, I added Fd, since the drag force is now being taken into account. To find b, I changed it until the final y value was equal to the final y value in experimental data. After making these changes, you can now see that there is an upward force on the object. The blue arrow represents the drag force, while the yellow arrow represents the gravitational force. In the new graph comparing the experimental position and the model position, you can see that the two overlap overall, suggesting that the model is a good fit for the data. The experimental position is still slightly underestimated, yet this could be due to the experimental errors. This graph shows the great difference between the computational model of just the gravitational force and the computational model of the gravitational and drag force. The fact that the blue line better predicts the yellow proves that the drag force exists. Terminal velocity occurs when the object is no longer accelerating due to the drag force being equal to the gravitational force. The graph of velocity is just the derivative of position versus time. It shows that the velocity in this interval is never constant and is constantly decreasing. Theoretically, the computational model with drag force will predict the terminal velocity, while the one with solely the gravitational force will not, but none of my models predicted the terminal velocity. If the object was initially thrown downward, the terminal velocity will still be the same, but it will reach it sooner. As you can see in this new computational model, the slope more visibly starts to flatten out compared to the slope of the previously discussed models. In conclusion, the model that includes drag force better predicts the experimental data because a falling object has two main forces acting upon it in the y direction, gravity and drag force. This concludes Lab 2.